Thank you very much, Silvana, for the presentation. And thank you for coming to this talk entitled Model-Based Supervisory Structure for Plan-Wide Control. I hope this proposal be a complement to the previously presented by the Professor Skogestad. The agenda today is, in the first term, the intention of this talk. Next, something about phenomenological based and physical models. After that, our proposal, a model-based supervisory structure for plan-wide control, with an example in brief. And finally, I will talk about our current work developed with the colleagues of the University of Salamanca, with one of my master's students. Okay. The intention of this talk. I want to explore with you three of the concepts that we have been working during these years. The first one is the physical plant parts versus the plant model parts, because the partition is a critical decision in plan-wide control. The second one is the non-explicit information from the process model, particularly with the kind of model that we use, because this information of the dynamics hierarchy is a guide for the partition of the plant. At the end, the collaborative control approach, which tries to use the process dynamic in order to collaborate to fulfill the plant or the process objective. We have now working in some possible extension with the people of Universidad de Salamanca. Okay, from plan-wide control to plan partition, and I want to use a site from this paper of Downs and Skogestad. The part of the interest is the purpose of this paper is to stress the need for a formalized yet simple approach that can encompass the many levels, this is very important, that arise in plan-wide control design. From recent publication, for me, this task is near to be completed, but still several opportunities exist. For example, the collaborative control to enhance the plan-wide control system. We are working in collaborative control in order to improve the proposal of Professor Skogestad and the other works. And in this sense, the plan partition is the base. If we have a good plan partition, we are the best opportunity to improve the control. Okay, the process partition as the base of collaboration. The fundamental view of the plant-wide control is the plant as a whole, but the plant is not a unique object. Several points of view produce different partition in the plant. And again, the critical item is the plan partition, because if we have a best partition of the plan, we can produce the best efficiency of the plan-wide control applied. The most common partition is the limits of the plan, particularly the pieces of the equipment in the plan. This is a direct physical separation. This is not the only possible partition. The plant is a complex object when mass and energy are interacting. One possible partition, we are using this partition, is the physical phenomena taking place in the plant, in this case for produce and hierarchy of the dynamics. The plan partition using this phenomena taking place in each process and in each piece of equipment may help to a better partition in order to apply plan-wide control. This is the base to construct the model of the plant, because we need to identify the phenomena causing the raw material changes or transformation in the plant as a whole. Therefore, the process model that we obtain has the capability of acting as a source of information for the plan-wide control. In addition, it is possible to include into the plan-wide control scheme some non-explicit information contained in the model available without solving the model. This is very important. Different to MPC, model predictive control, than we need to solve the model each step. Let me talk about three or four definitions, free definition about process, pieces of equipment, and plant that fulfill the requirement to form a common field to talk about our proposal. A process, again, is a free definition. A process is an abstract view of one or more phenomena taking place to produce a desired raw material change. This is the first definition. The second one, a piece of equipment is a physical place. Know the difference? In the first case, this is abstract view, and this is a physical place where one or more processes are being executed. And the third definition, a plant is an arrangement of pieces of equipment where phenomena are taking place, obviously inside the pieces of equipment. Therefore, the model of the plant is the integration of individual models of the process, this is abstract, affected by operative condition of the pieces of equipment, this is physical, where the process are taking place or are occurring. Okay, what partition to use in plan-wide control? Again, the borders of the pieces of equipment are the common partition used in plan-wide control. This is not the natural partition because the basic interaction is not among pieces of equipment, it is among phenomena. And this interaction is our key to perform some collaboration among the dynamics in the plant. How each phenomena could help to other phenomena taking place in the plant to fulfill the desired behavior for the whole. This is the question to be answered with collaborative control. The answer obviously is by collaboration, but this collaboration is not inherent. This collaboration must be induced from the control structure, from the supervisory level and the control structure. A difference is required to talk about the collaboration. Collaboration is not cooperation. This is a difference. Cooperation occurs among equals. For example, we have a robot's team because all are the same machine. But in chemical process, we have collaboration because collaboration implies different participants, different process dynamics like temperature, flow, level, pH, etc. Due to the importance of the model in our proposal, let me talk about a kind of models that we call phenomenological-based semi-physical models. As we know, any model contains knowledge, but different kinds of model contain different amounts of knowledge. With a white box model, we guarantee that the maximum knowledge is possible in this kind. But contrary, a black box model contains the minimum knowledge possible. And the question is, are the black model useful for all tasks in engineering? And the answer is no. No, because this model has several restrictions due to the data used for its or their identification. Therefore, the white box seems to be the option to use because the model structure is easy to find from conservation principle. But to find parameters from laws, principles, or theories is so difficult in this kind of models. Therefore, we propose to use a mixture or gray box model with the best knowledge content capability, and we have two options to use this kind of model. The option one is to take the structure of the model from the black box and to use parameters from the white box. This is called the empirical-based semi-physical model. But this is a poor choice because the structure is so fragile from the black box model, and in addition, to find parameters from white box is very difficult. Therefore, we have only one option remaining, and we call this phenomenological-based semi-physical model. Phenomenological-based because the structure is taken from the white box or from the phenomena taking place, and the parameters from the black box as submodels. How to obtain a phenomenological based semi-physical model? We have a proposed routine in permanent refinement to construct this kind of models. And some history all begins 20 years ago when I was trying to model an activated coal pilot plant to control it during my master studies. And the proposal is inspired in several works about modeling, from seminal works like the Aris book, and to modern works like the Hangos and Cameron book. The procedure is a collective construction with contribution from students and professors working on our research group on dynamic process modeling. This is the name of our group, or Kalman group. And around 15 theses of graduated students have used several versions of these procedures, theses of master and doctoral. The routine is published in 2 papers. The first one with my friends and colleague here, Rosalba, Silvana, y Pastora. And the last one with one of my doctoral students, Elizabeth, and my colleague at the National University, Diana Lopez. In briefly, this routine has only 10 steps. The first one is to formulate the questions to be answered by the model. This is very important. What do you want to model say about the process? And a verbal description, obviously with the process flow diagram, complement each one in order to describe the process that we are trying to model. The step 2 consists in propose a modeling hypothesis. A modeling hypothesis is a brief description about what do you think is taking place in the process in order to formulate some mathematical equation from balance to this phenomena. And set a level of detail. This is very important because the level of detail determines if you can reproduce some parameters of the process. Step 1 and 2 are a loop in order to improve your description and you decide about the model. Step 3, define as many process systems on the process to be modeled as required by the level of detail. The process system is directly taken from the Hangos and Cameron proposal. A clue to determine process system is look for 1, physical walls into the process, 2, distinguishable phases, and 3, any mass characteristic marking spatial difference in the process. When the process system are determined, it is required to plot a block diagram relating these blocks, use the mass and energy flows as connection. Step 4, apply the principle of conservation on each defined process system. It is recommended to take at least the next balances of the total mass balance, in component mass, and the total energy, thermal or momentum in the process. This equation form the dynamic balance equation, dBE, including some momentum balance possible in stationary state. Step 5, select from the dBE those equations with significant information to fulfill the model purpose, as it was established in step 2. They form the model structure. Again, some dBE can be a stationary equation, but are included into the model. Other dBE are redundant or merely a numerical equality, then they must be discarded. Step 6, identify variables, parameters, and constants on the model and fix all constant values of the model. The variables are those values that you need determined from the model, cannot be determined a priori. And parameters will never be the result of the model solution. You must specify these values or submodels to calculate these values. Step 7, find constitutive equations for calculating the largest number of parameters in each process system. Parameters without a constitutive equation must be identify from experimental data or determine from auxiliary models. This is empirical swan models, normally black box. Step 8, verify the degrees of freedom, df, of the model. Remember that the model is a mathematical structure or system, and you need that df be 0 in order to have a solvable model. Step 9, build a computational model, a computer program able to solve the model without altering the true mathematical model response. And step 10, and the end, validate the model response using real operating condition related to those used in step 2 for establish the model object or the question for the model. Final comments about phenomenological based semi-physical model, this procedure. It tried to easy to follow and intuitive to be a short procedure help because we have only 10 steps. Enough previous knowledge about the process is required, but not much to be an expert on the process. Steps as determine the controlling mechanism in the process are not intuitive. Therefore, we don't introduce this kind of step into our procedure because requiring expert judgment about the process. Okay, I take a minute to explain the modeling in order to propose this structure because this structure is based on this kind of model, on semi-physical based models. This is our proposal. It's not a proposal different to Skogstad proposal. For us, this is a complement in order to introduce the benefits of the model of this kind of model, phenomenological base, into the plan-wide control. Okay. About plan-wide control proposal, the majority of plan-wide control involve model predictive controllers, MPC, and this conduces to less flexibility and less simplicity in the proposed control structure. Other control strategies involve the decoupling of interactions among units, which require most complex models inside the controller. In brief, the major drawbacks of the available plan-wide control structures are 3. The number 1 is very complex structure. The 2, hard communication demands among controllers. And finally, the high computing requirements in order to evaluate the model of the plant. Our proposal looks for a control structure with good performance but simple structure for its implementation in industrial environments. In this sense, we select PID controller, consider the simplicity of this structure and the current industrial practice, which prefers the operation of the existing facilities in new ways instead of change the facility or introduce new equipments. The partition used in this proposal, obviously, is a hierarchy of the process dynamic evaluated for the Henkel matrix, which consider the input variables as a whole over each one of the state variables of the process. In this way, we obtain an index that we call a state impactability index. This index evaluated from each one of the state of the plant and consider that the larger is II represent the main dynamic of the process and the other represent the secondary dynamic of the process, permit to construct a hierarchy of the dynamics in the plant. After that dynamic partition is made, the control loops of the main dynamic is the only one maintained in regulation mode. The rest of the controllers are turned to tracking mode, operating tracking mode. This is a change regarding our current practice in chemical processes. The hierarchical approach uses 2-layer control structure. The regulatory layer or flow layer contains the main dynamic and the secondary dynamic control loops. It is the frequent at the practice in plan-wide control. And the secondary dynamic, the supervisory layer, is in charge of optimize the set points of the secondary dynamics controller in order to minimize the deviation of the main dynamic, reducing the control efforts. What is the philosophy and operation of the proposal? The effect of every secondary dynamic over the main dynamics is exploited and explicitly extracted from the process nonlinear model offline, non-inline, offline, without solving the model. A collaborative approach is used for secondary control loops coordination. This is the secondary dynamic set points are selected in an optimal way in looking for the main dynamic can be easily regulated, the only one regulated in the plant. The goal is to profit all the knowledge contained in the phenomenological base model of the process, but directly in a cost function structure, known by simulation. This is the main tool of the optimization. In this way, a sensitivity-driving coordination criteria is proposed as cost function without requiring the solution on an optimal control problem at future time, in MPC, different to MPC. At each sample time, cost function terms are evaluated from this time only, no future time, at the current condition of the process. Direct information exchange among controllers is not required. Time to calculate complete control action to be applied is very short. The process dynamic behavior is completely considered because we use the model of the plant. Process information is preserved, different from decentralized or distributed control structure when some of the process is lost. Okay, the coordinator cost function, J, this is the core of the proposal. For any supervisory control, a model of the process and an adequate objective function are required. The process model, in this case, is a phenomenological-based semi-physical model. We use this kind of model. And using an objective function based on this kind of model, we obtain a model control structure simple. The cost function J is included into an optimization problem of the secondary dynamics set point. And this cost function has in the first term the possibility of following the set point of the main dynamic. This is the super start variable. And in the other terms, the cross sensitivity among the secondary dynamic and the main dynamics. The first term corresponds to the main dynamic steady state value achieved when the process reaches the steady state corresponding to the values of the secondary dynamic set points found by the current optimization. This value is calculated from the steady state map of the process, obviously from the nonlinear model, and offline, is not online, is offline. These values are the minimum and maximum controllability limits for the secondary dynamics in order to perform the optimization when we want to obtain the main dynamic value. Those values are extracted from the reachable set of the process. A reachable set are all the points in the steady space to which a system can be driving at a given time from its current point using the available control inputs. This is a picture about one of our evaluated or calculated reachable sets at different time, from 0 to 22 time units. For enough long time, a map of steady state is obtained with this reachable set. Si corresponds to the sensitivity of the main dynamic to the changes on the secondary dynamic, in this case the I secondary dynamic, at the current value of the process state. Such function is obtained directly from the process model by differentiating the main dynamic over each one of the secondary dynamics from its corresponding equation in the model. This delta value are the maximum and minimum possible changes in the secondary dynamics set points. Admissible changes for these secondary variables are obtained with the manipulated variables of the process. Alpha is a weight from the main dynamic error, is a tuning parameters. Beta is an scaling factor for the sensitivity, is a tuning parameters too. And the constraints ensure the control system ability to drive the process to a new admissible set point. In this way, controllability and stability of the process are considered in the supervisory layer when we are determining the secondary dynamic set points. This procedure uses the steady state sensitivity, avoiding dynamic optimization. We don't need a dynamic optimization. This conduces to a computing requirement low and executed at each sample time. In addition, we obtain a PSY optimization trajectory because obviously each step was optimized. Some characteristic of the objective function, contrary to optimization performed by model predictive controllers and optimal controller, the disturbance effect is known since at each time the structure, the current state measurements are used to compute the sensitivities. We know information at time. Current measurements are updated to account for the dynamic process evolution used in the optimization from the next step of the control. For obtaining the main dynamic sensitivity, the process model, the nonlinear version of the process model, is used with explicit differentiation to preserve its information contained. In this way, we obtain and exploit information non-available from model solution. This is non-explicit information. And finally, we can use some trigger because if no disturbance is affecting the process, to change the secondary dynamic of the process will not be necessary. Some triggers or proposal of trigger to use are the deviation on the value of the cost function. For example, if the deviation is greater than 5%, or the deviation of the main dynamic set points at some value, for example, 1%. Let me illustrate our proposal with an example in brief. This plan is used frequently as a benchmark for plan-wide control. Professor Skogestad shown the same plant in one of the presentation. The example is treated in detail in this paper with two of my master students. The plan has the typical reactor, recycle, and separator configuration. The process illustrator is this. We have a continuous stir-tank reactor, a flash drum, ensures of separate the liquid and vapor. The vapor is part of the reactive that return after the condenser to the reactor. A mixing point to feed new reactive, and a main heat exchanger and two auxiliary heat exchangers. The reaction is a catalytic hydrolysis of propylene oxide in aqueous solution to produce propylene glycol. The propylene oxide is the reactive and propylene glycol is the product, A and B. The phenomenological based semi-physical model of each unit will be presented independently for easier comprehension, but the proposal uses the model as a whole. Remember this. For the reactor, we have 4 differential equations obtained from mass balances. The first one, a balance for the reactive, the second for the solvent, in this case water, the third one for the product, and the last one is a energy balance for the reactor temperature. For the flash separation drum, the 3 dynamic equations are are taken from mass balance in this case. The first one from the reactive, second one from the water or solvent, and the last one from the product. And from the heat exchanger, the main heat exchanger, the equation is obtained from the energy balance, a total energy balance, and obtaining the temperature of the reactor input. The mixing point is an static model. All variables predicted at the exit of the mixing point. The first one, reactive, the second one, the solvent, concentration, third, for the temperature after the mixing point, and the last one, the flow produced in this mixing point. Okay, the variable pairing was executed using the procedure of Skogestad, nothing different to the proposed in the literature. And the intention was using the control loops existing in the plant, the pairing from the manipulated variable U to the 3 controlled variable was maintained. No changes were applied. We have one the first control loop is the input temperature to the reactor. The second one is the product concentration, which is a cascade control among concentration and temperature. And the final control loop in the plant is the reactive concentration in the liquid stream leaving the flask drum. The previously calculation to apply our proposal, the first one is to evaluate the state impactability index for variables of the plant. We use the Hankel matrix, and this is the record of the index for all the variables in the plant. Obviously, the first one will be the main dynamic, but take care because since no vaporization occurs in the column in the flask drum, we can use the second variable in the state impactability index and as the main dynamic or the control objective. In this case, the concentration of the product in the reactor. This is our main dynamic. And the other with control loop, will be our secondary dynamics. In this case, the concentration of the reactive in the liquid stream of the flask drum and the temperature on the input to the reactor. The remaining variables are secondary variables because don't have control loop or are into the cascade structure. Because we have one main dynamic and 2 secondary dynamics. The first structure tested was a decentralized control structure, the original control structure in the plant with 1 cascade. All PID controllers operating in regulation mode with fixed set point, as we use in chemical engineering. And main dynamic, the concentration of the product in the reactor, propylene glycol concentration, is maintained. This is the cascade, and this is our only set point available for the other proposal. In this proposal, all the set points are free from temperature here and the concentration here. Okay, and this is our proposal hierarchical control or collaborative control. In this way, we have only 1 set point available. This is the only one because the other set point depends on the coordinator decision. The main dynamic, obviously, is the concentration of the product in the reactor. The secondary dynamics, the concentration of the reactive in the column flask drum, and the temperature at the input of the reactor. Okay, sensitivity function pre-evaluated from using other format of the model, in this case a graphical format from interaction, called directed graph. The first one is the sensitivity of the main dynamic regarding the secondary dynamic of concentration, and the second sensitivity is the changes on the main dynamic regarding the temperature in the input of the reactor. Controllability limits values for the secondary dynamics are numerically calculated from the reachable set The reachable set is obtained offline, evaluated, and this is a three-dimensional volume, as it's shown here. We use 3,000 minutes of simulation for each point in order to guarantee the steady state, and use admissible control inputs with a uniform distribution, taking 35,000 points to construct this volume. And the question answered by the model of the plan was that given a pair temperature and concentration as known value, and setting the manipulated values with this distribution, what is the value of the main dynamic at the steady state? And this is the volume obtained. Obviously, to use the volume is very difficult. We use views in two-dimensional views of the reachable set, fixing one of the secondary dynamic. In this case, on the left, the constant value was for the concentration of the reactive, and in the right, the temperature was fixed. Obviously, we need smoothing the contour to obtain some function for evaluate the limits of the controllability on the secondary dynamics. This is the limit to move the secondary dynamics during the optimization, which depend on the main dynamic set point, which is fixed. Okay, let me show some simulation results using the two control schemes, the decentralized or original control scheme in the plant, and the collaborative or hierarchical, our proposal, as the new control structure. We compared the two control schemes using two disturbances on feed concentration to the reactor. The PIDs for both control schemes have the same tuning, no modification on the tuning of the controllers. And the cost function used and the constraints are these. Again, the first term is in charge of maintaining the set point of the main dynamic, and the remaining terms are used to evaluate the sensitivity of the main dynamic regarding the secondary dynamics. It's important on the constraints, the first and second constraints are the controllability limits for the secondary dynamics associated with the set point of the main dynamic evaluated from the reachable set. Offline evaluated the function with the contours, and online evaluated these limits with the function extracted of these contours. And the last two constraints are related to the rate of change on the secondary dynamics of the process using the capability of the final control elements, manipulated variables. The first result illustrates the behavior of the main dynamic, in this case the product concentration at reactor outlet. In blue line we have the decentralized structure, and with discontinuous red line our proposal, hierarchical or collaborative. Here we apply two disturbances. The first one is a reduction of 9.5% in the feed of the concentration, and the second one is an increment of 30% in the feed concentration to the reactor. As can be seen, after the first disturbance, the overshoot is more or less the same for the two proposals, with a different movement regarding to the set point variation on the secondary dynamic. But after the second disturbance, the overshoot of the hierarchical or collaborative structure is less, and the setting time is less too. This is due to the changes on the set points of the secondary dynamic. This is the one secondary dynamics, in this case the reactive concentration at column liquid outlet. And you note for the decentralized, the set point is fixed, but with our proposal, the set point of this secondary dynamics was changed after the first disturbance. In this way, we obtained a better performance in the system. This is the set point change, and obviously less overshoot was produced, but this is a secondary dynamic. It's important to note that the trigger is required here. This trigger is required because we have some variation, less variation of the set point undesirable. This is the other secondary dynamic. Obviously, the set point changed too, and less overshoot and less oscillation was obtained with the hierarchical, but remember that this is the secondary dynamic, not the main dynamics. And the setting time is less too. And again, the trigger requirement, because we have some variation in the set point, undesirable. The auxiliary variables, in this case, the temperature in the reactor, this is a slave variable. In the decentralized, compared with hierarchical or collaborative control, the operation is at low temperature when we use collaborative control, and less overshoot and less oscillation are presented during the operation. And the final secondary dynamic, the jacket temperature, again, less overshoot and less oscillation are obtained when we use the hierarchical or collaborative control structure. Obviously, less settling time and less control effort. Let me show the performance indexes, a comparison of the two decentralized and hierarchical proposal structure with index from the error, the absolute and temporal evaluation of the error, and from the control effort, again, absolute and temporal absolute evaluation. The hierarchical or collaborative produce ever difference regarding the decentralized. Very good difference for me, 40%, 55%, again. And we use an index proposed in this book for the deviation on production target and the plan as a whole. This index is an integration of this difference between the desired and production rate during all the time execution of the process. And this index is very interesting because was reduced 55% compared with the decentralized structure when we use the hierarchical or collaborative control using these two disturbances previously illustrated. Okay, let me finish with our current work, which is in develop with our colleagues from Universidad de Salamanca. We are trying to fulfill this problem statement. The previously proposed methodology is not useful for all possible cases of control in chemical processes. For example, if you have the possibility to manipulate some parameters to improve the control performance, this methodology is not adjusted to use in this case. But this methodology can be used as the base from propose an extension in order to manipulate these variables, controllable parameters, using the hierarchy and the state impactability index proposed. A free definition, we are working on it. A control parameter is a process parameter with the option of being directly manipulated using one or more control actions. If a control loop can be installed from a controllable parameter, an extra degree of freedom is obtained, and obviously we can improve the plan-wide control structure. Our hypothesis is including the controllable parameters into the objective function of the collaborative control strategy will improve the process control. And we are working in mass transfer controllable parameters. In a aerator reactor, the oxygen concentration is controlled manipulating the quantity of gas supply. This is the U, or manipulated variable. But the mass transfer is not described for this quantity. The mass transfer is described by a gradient law with the product of the mass transfer coefficient, KL, and the mass transfer area. KL and A product is assumed as the manipulated variable in this structure and the current common structures, but two controllable parameters exist, the coefficient and the area, and we can manipulate both. This is a typical configuration of a treatment plant, wastewater treatment plant, and we are applying in the last one reactor, but our intention is to extend to the plant as a whole in the plant-wide control as collaborative control. From the process configuration, it is evident that mass transfer coefficient can be manipulated, changing the airflow, and the mass transfer area can be manipulated, altering the air supply pressure, because we obtain a bubble of greater than the original. Obviously, we have cross effects, undesirable cross effects between these two manipulated variables, and this is our challenge. We are working on it. An extension of collaborative control is our proposal, and we are working on these topics. A procedure to evaluate the cross-sensitivity of the main dynamic regarding controllable parameters. To add this cross-sensitivity of the main dynamic regarding controllable parameters into cost function, this will produce two new terms or more new terms, and obviously new variables to be considered during the optimization of the cost function. To develop a tuning procedure of new degrees of freedom, because the controllable parameters are new degrees of freedom gained from the inclusion of these parameters in the control structure, and test and compare with the centralized or collaborative without considering controllable parameters in order to determine the improvement of the use of these parameters into the control structure. The model used is the BES M1, Alex et al. This is the use water treatment plants benchmark in control proposals. Okay, this was my presentation. Thank you for your attention, and some questions or comments are welcome.